Hello there, students and friends. Today's episode is focused on analyzing problems involving change in entropy and the second law of thermodynamics. How do we determine the change in entropy for reversible and irreversible processes? Find it out by watching this video till the end. Just hang on, watch and learn. Question number 1, which is about change in entropy of an ideal gas. Initially, 5.00 moles of helium, which we can treat as an ideal gas, occupies volume 0.120 meter cube and is at temperature 20.0 degrees Celsius. You allow the helium to expand so that its final volume is 0.360 meter cube and its final temperature is also 20.0 degrees Celsius. Question is, calculate the net change in entropy of the helium if you make the helium expand isothermally from 0.120 meter cube to 0.360 meter cube. For our solution to this problem, we first list down the given quantities. We have the number of moles, small letter n equal to 5.00 moles, the initial volume V naught, 0.120 meter cube, the final volume, capital V, equal to 0.360 meter cube, the initial temperature, T naught, 20.0 degrees Celsius, and our target variable is the delta S, or the change in entropy of the gas. So this is an example of an isothermal process where the system or the helium gas expands at a constant temperature. So if the temperature is held constant, we also say that the expansion of the gas is an isothermal expansion. Okay, whose formula for determining the change in entropy delta S is of course equal to big Q divided by the absolute temperature T naught. All right. Before we can calculate for delta S, we need to know what the heat, capital Q, is. All right. And using the equation for the first law, all right, the first law of thermodynamics states that the heat Q, or big Q, is just equal to the sum of the change in internal energy delta U and the work done, capital W. Right? But we will first calculate for the work done by the gas using the formula W equal to the number of moles, small n, multiplied by the gas constant, capital R, times the initial temperature T naught and the natural log of the ratio final volume divided by initial volume. So plugging in the given quantities to this formula, we get 5.00 moles times the gas constant 8.314 joules per mole Kelvin, then multiplied by the equivalent temperature in Kelvin, of T naught, which is 20.0 degrees Celsius, that is 293.0 Kelvin. And then the natural log of the ratio 0.360 meter cube divided by 0.120 meter cube. So doing our math, we will get the value of the work done, capital W, equal to positive 1.34 times 10 to the fourth power joules. All right? Since the change in internal energy, delta U, is zero in an isothermal expansion, all right, we can proceed now in determining the heat big Q, which is just equal to delta U plus the work done W. And since delta U is zero, we just uh, add to delta U the amount of the work done, 1.34 times 10 to the 4th joules. In other words, the value of the heat capital Q is equal to positive 1.34 raised to the 4th power joules. All right? So, to find the entropy change of a system that goes through a reversible thermodynamic process at a constant temperature T, we just divide the heat that flows into the system. All right? This heat flows into the system because it has a positive sign. So, the formula for determining the change in entropy, stated earlier as delta S, equals big Q divided by the initial temperature in Kelvin, which is T naught. All right? That is, we divide the value of big Q, positive 1.34 raised to the 4th power joules divided by 293 Kelvin. This is the Kelvin equivalent of 20.0 degrees Celsius. Again, simplifying, all right, we will get delta S equal to positive 45.7 joules per Kelvin. All right, since the heat flows into the system, all right, such that Q is positive, it follows that the change in entropy, delta S, is also positive. And we say that the entropy of the gas, all right, has increased by this amount, all right, 45.7 joules per Kelvin. Or we can say that the degree of randomness of the system has indeed increased. Moving on to our last question, question number 2. You combine 1.00 kilogram of ice whose heat of fusion is equal to 3.34 raised to the 5th power joules per kilogram at 0.0 degrees Celsius and 0.839 kilograms of liquid water whose specific heat is 4.19 raised to the 3rd power joules per kilogram Kelvin at 95.0 degrees Celsius. When the system comes to equilibrium, all of the ice has melted and the temperature of the mixture is 0.0 degrees Celsius. Question: calculate the change in entropy for letter A, the ice as it melts, letter B, the water that was initially at 95.0 degrees Celsius, and question letter C, the change in entropy, right, of the combination of the two. Also, does the net entropy of the system increase, decrease, or does it stay the same? For our solution to this problem, we identify the given quantities. For the ice, we are given the mass equal to 1.00 kilogram. Its initial temperature T0 is 0.0 degrees Celsius. During melting, the temperature of the ice remains constant, so we can say that the final temperature is also equal to 0.0 degrees Celsius. In the case of water, its mass is given 0.839 kilograms at an initial temperature T0 equal to 95.0 degrees Celsius. So when the water cools down from 95.0 degrees Celsius to 0 degrees or 0.0 degrees Celsius, uh, this is the temperature when the water and the ice are what we call in thermal equilibrium. All right? So our target variable is the delta S, or the change in entropy for each substance, the ice as well as the water. Now, melting of ice is an example of a reversible process because uh, even if there is amount of heat being absorbed by ice, all right, its temperature remains constant. And the formula for determining the change in entropy for any reversible process is simply delta S equal to uh, the amount of heat Q divided by the absolute temperature T. All right? And so, uh, during melting, the amount of heat that is absorbed by ice at constant temperature is simply the product, all right, the product of the mass of ice, given here as 1.00 kilogram. Okay, when that is multiplied to a constant known as the heat of fusion for ice, which is also given in the problem, 3.34 raised to the fifth power joules per kilogram. All right, and since uh, heat Q is into the system, meaning it is being absorbed by the substance, ice, all right, we denote that Q with a positive sign. So if you are going to divide that by the constant absolute temperature equal to 273 Kelvin, the whole thing will be the change in entropy for ice. All right? So doing our math, that delta S for ice is equal to positive 1.22 raised to the third power joules per Kelvin. It is positive, which means that there is an increase in the entropy of the ice while it is absorbing heat, all right, with no change in temperature, but its entropy is increasing by as much as 1.22 times 10 to the third power joules per Kelvin. And for question letter B, all right, in the case of the water, whose initial temperature is 95.0 degrees Celsius, and the final temperature being the thermal equilibrium temperature, which is 0.0 degrees Celsius, such process of cooling down from a higher temperature to a lower temperature is considered an irreversible process. All right? And we cannot make use of the simple formula for determining the change in entropy that we use in the case of ice. All right? Because here there is now a change in the temperature. All right? We use instead a formula for delta S that is derived using integral calculus. All right? And the result of integrating, all right, is this formula here. All right? Delta SW is just equal to the product of the mass of water multiplied by its specific heat, which is also given in the problem, and then we multiply it to the natural log of the ratio, all right, the ratio of the final temperature, capital T, over the initial temperature, T naught. So both T and T naught are in Kelvin temperature. So substituting the given quantities, we have 0.839 kilogram multiplied by the specific heat, water 4.9 or 19 raised to the third power joules per kilogram Kelvin, and then we get the natural log of 273 Kelvin divided by 368 Kelvin, and doing our math again, we will get the delta S for water, or the change in entropy, equal to negative 1.05 raised to the third power joules per Kelvin. So in the case of water cooling down from a higher temperature to a lower temperature, we have a negative delta S, which suggests that the entropy of water has been decreased. All right? It has been decreased, mathematically speaking. Why the negative sign came out? Because the result of getting the natural log, all right, of a number that is less than 1, if you divide 273 Kelvin by 368 Kelvin, it will be a fraction less than 1. And natural logarithm, or the natural log of a number less than 1, will result to a negative value. All right? So that's why we get here a negative delta S. And finally, moving on to the last question, letter C, which is simply asking for the net change in the entropy of the two substances, the ice and the water. Okay, so we get the formula for determining the net change in entropy, of course, is simply to add the two delta S for ice and for water. That is positive 1.22 raised to the third power joules per Kelvin. That's for ice, and then negative 1.05 raised to the third power joules per Kelvin, that is for water. So we get the net change in entropy, the system consisting of the ice and the water, equal to positive 1.70 raised to the second power joules per Kelvin. So, for the combined, what we call system, the ice and the water, we say that the change in entropy is positive. And this indicates that there is an increase in the net entropy. All right? There is an increase in the net entropy for the system. So that's it. All right? We are done with our tutorial. Till our next episode. But for now, thank you very much. Inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.